So that's the first bit. What is phosphorus and why is it important? So now to the next bit, soil to plant mobilisation of phosphorus. Really, why do we do that? So, well, let's just look at this really. It's really elementary agronomy, but it really is very important for getting the message across. Basically, it's absolutely amazing in helping in plant and crop production, and therefore in feeding the planet. So the extractable soil phosphorus along this axis here, we measure different types of those. They could be called Olson's phosphorus or Bray phosphorus. Just call it available phosphorus. That's all you need to know. And the yield of plants is just correlated. Okay. And here's some real data. That's a kind of conceptual version. The real data here is Olson's phosphorus, which is this available phosphorus by this scientist developed by the scientist Olson. He would extract it from soil. And Olson has showed the data showed for wheat production here that if you increase the Olson's P up to a certain level, about 20 to 30 milligrams per kilogram of soil, that the yield of wheat grain increases. And after a while, above a certain level, it flattens out. And the same here. I can't see very well because I've got my video images in front of it, but it's the same for grass yield. The same principle applies. So basically, the simple point is, from an agronomic point of view, and the point of view of agronomy or agriculture or crop production, it's really helpful. And if we mine it, we take it around the world, and we distribute the fertilizer on land, it really helps in that productivity. It's often it's really an overlooked, or I feel one of the neglected nutrients. Nitrogen and carbon sort of attract more attention in terms of global biogeochemistry, but my argument and our argument in the book is that phosphorus is really one of the hidden important issues, important elements for our global biogeochemistry. So to this next slide, which is supposed to be a picture, there it is, a picture of a tractor spreading fertilizer, and just to really help remind us of, this is actually my neighbour spreading phosphorus fertilizer on their dairy farm, and just to remind us really of this process of distribution and use of phosphorus in agriculture and in soil. Let's have a little look now into the soil and have a little bit more of a detailed dig into what's going on in the soil system. So if, for those of you who are interested, as you go through your degree, you have the option of taking Lec 278, where we will really get into these processes a lot more. That's the Lec 278 is called Soil Science, and we do quite a bit of phosphorus on there, as myself and John Quinton. And the kind of point is that here we have the kind of conceptual plant and the soil solution, the actual bit which is mobile to the plant, and then we have all these processes which govern the mobility in and out of solution, and therefore the mobility in and out of the plant. And there's all sorts of issues like adsorption, desorption, in and out of the different mineral forms or organic phosphorus forms or whatever there are. Another schematic here shows you a typical phosphorus balance for a developed piece of agricultural production system, typical system of a dairy farm in the southwest of England, but really an exemplar of many parts of the productive agriculture around the world. And here, what we show here is an example of the phosphorus balance on a modern farm. And the balance, the very simple point is that typical inputs are about 58 or 60 kilograms of phosphorus per hectare to this dairy farm that Haygarth et al. Studied, and that the outputs were around about 33 kilograms of phosphorus per hectare in terms of the outputs to the farm, and there's different components to that. But the simple point is that over time, that the inputs are greater than the outputs, and if that's happening, think about it, it's going to accumulate in the soil. And indeed it does, and this is what happens when we study underneath permanent pasture, underneath dairy soil. We can see that the Olson's phosphorus, this measure again of the available P in the surface soil, accumulates right near the surface, and that it then sort of, as you go deep down under the soil, so this is the soil surface, the Olson's P here, different examples here, it basically falls off very quickly, and it's very rich, very much enriched near the soil surface. So really making the point that there's a lot of P sat at the surface of soils, and that just remember that point when we come to talk about the later parts of the lecture, when we're thinking about transfers to water, because that that makes it very vulnerable if there's a lot of it close to the surface where we have the runoff going on, and it's called the effective depth of interaction for the runoff. So all this phosphorus comes in, builds up in the soil surface, and then sort of stays there, and it's vulnerable to perhaps wash off and run off, but also very readily available and useful to the plants. So just for those real specialist and interested chemists, actually you don't really need to learn all this, but you need to be aware of this. There are all sorts of different chemically stable forms which exist in the Earth system and in environmental samples and in soil and in and around plants. The most commonly stable form of phosphorus is phosphate, the oxidized form, and that's typically, well, that's an inorganic orthophosphate. There's also pyrophosphate and polyphosphate, are all organic oxidized, inorganic oxidized forms of phosphorus. But also of interest is the fact that there are other compounds which are called organic phosphorus compounds. They're organic in chemical constitution rather than organic in the kind of organic farming style way. And these organic monoesters, chemical monoesters, dioesters, phosphonates, or other types of organic structures tend to accumulate in soil after years of phosphorus application to agriculture. So what you find if you study ecosystems over the long term is that these organic forms start to accumulate and dominate, take over the soil. Next slide. This is a study that my colleague Mark Stutter led from the James Hutton Institute in Scotland, and showed that the inorganic orthophosphate, the blue, those are the oxidized forms. They definitely dominate in sort of world soils. But there's also this really intriguing organic forms, the monoester organic P, that's the red, and the diester organic P, that's the green, and they definitely form a substantive component of what's available in soils. This slide here shows that in even more detail. What Mark did, what we did as a team, is we surveyed 32 agricultural soils across England, Wales and Scotland, and we extracted the sodium hydroxide EDTA, the organic phosphorus fraction, using that extractant. And for all of those soils we found, remember this inorganic organic P thing, we found that 59%, let's call it 60 for the sake of argument, there or thereabouts, 60% of the soil total phosphorus was organic, and it actually ranged from 16 to 93. But if you took It's really interesting this if you just stop and pause and think about it. Spend a minute on this. If you take a grassland, this is a grassland here, the total phosphorus in that grassland soil, the total, all of the forms, inorganic, organic, blah, 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 all the forms, everything is, in this example, was 1233 milligrams per kilogram. The Olsen's P, that's the agriculturally available form, was 43 milligrams per kilogram, which represents 3.5% only of the total. That's all it is. But this is the bit which all the agronomists are getting excited about, that the plants are using, but it's only that out of that. Isn't that amazing? And yet the organic P, this form which is sort of ignored really, constitutes about 60%, of the total, which represents a potential resource if we can use it. And there's a sort of similar but less extreme example from arable soil. So that's grassland, and arable is cropland, and grassland is animal grassland really. And then the cropland, because that receives even more fertilizer, it's a little bit less extreme. So this particular soil had 1475. There was 84 milligrams per kilogram Olsen's P, but it was nearly 6% of the total, but still only a tiny portion of the total, and represented about 41% of the total. Isn't that amazing? And actually I calculated that on the back of the envelope that about 44 million tonnes of phosphorus in UK soils, out of that component, a substantial amount would actually be organic. So moving to the next slide, this is just a slide which shows us it's a nice schematic really of what we call, and you'll learn more about that as you go through your degree paths. If you take this journey, it's the kind of importance of the plant, and the plant has a rhizosphere, this zone around the root mass that's part of the soil, and in this rhizosphere the plant gives out all sorts of funky little chemicals which are very clever at breaking and accessing different forms of nutrients, in our case phosphorus. Not only that, we have symbiosis of mycorrhizae fungi which give out a bridge from the soil to the plant to help the plant access the phosphate. And we also use other things called enzymes and organic acids, which are all part of the story. So the point for this lecture is that plants have clever mechanisms for getting it if they really need to or really want to. But that's perhaps another challenge for another day, but just factoring that into your mind in your understanding of what's going on. And so in terms of this organic phosphorus, just to sort of give you a little bit of the social side, me and my wider cognoscenti of colleagues, I organised an organic phosphorus workshop in the Lake District in 2016. There's about 100 top scientists, professors around the world came together to discuss and seek out the curiosity of understanding what's going on with the organic phosphorus forms, and to try and ask the question, can we do more about releasing that and using that for our betterment really. So let's just stop and pause. We're kind of we've done the first two here, and we're about to move on to the next two. So what I've done is I've told you about the importance of phosphorus. We've considered the fact that the Earth is 4.5 billion years old, and